Hello, it is Dr. Lou. In case you have not watched the prior videos, I am the lead faculty member who has created the online laboratory classes using the kits from Science Interactive. In today's video, I'm going to go over how to calculate the kilocalories in the burned food. Also, I will briefly discuss some of the things to pay attention to in the procedure. This experiment is all about calculating the caloric content of food. I think the procedure online is very straightforward, so I am not going to spend that much detail or time discussing the procedure. What I want to do is to go over the calculations with everyone, because I believe most people collect the correct data, but we have problems when it comes to the calculations. So to my left is some sample data for the experiment. I have mass of water, I have the weight or mass of the food burned, and I have the temperature change of the water. So what we're going to do in the experiment is burn some food. As we burn food, heat is released. That heat is going to warm some water inside a pop can. We can measure the change in temperature of the water inside the can and calculate the heat absorbed by that water, which will be the opposite of the heat given off by the food. So we can say that Q is going to equal to what? Heat. Okay, so Q equals to heat. So we can say Q of H2O equals negative Q for your food. So when the food burns, it gives off energy, and that energy heats up the water. So let's look at the formula for specific heat. So the formula for specific heat, heat Q is equal to mass times specific heat times our change in temperature. I will move this formula up to the top and leave that there. So in this experiment, we are measuring a weight of water. We are measuring a temperature change of water. So we are going to say that Q, H2O, or water, is equal to mass H2O. The specific heat of water is 1 calorie per gram degrees Celsius. And then we have change in temperature of the water. Okay. So there is the specific formula we are going to be using when we are talking about the water. On the data table, I have simplified everything. So you will be measuring weight of water in the pop can. Then you are going to need to determine the weight of the food burned. So the weight of the food burned is going to be the mass initial for your food. And let me move that over. Give me one moment. So the weight of food burned is going to be mass initial minus mass of your final. I went ahead and already provided you the weight of food burned because I think this calculation is very straightforward. Same thing is true for change in temperature. So delta T equal to T final minus T initial. The reason why we put the initial food weight first is so that we end up with a positive value for the weight of food burned. Okay. Do pay attention when measuring the weight of food and the change in temperature. I'm going to write do not forget estimated digits. So when reporting measurements in the data table, you must always include the estimated digit. Let us do a sample calculation. So I'm going to calculate Q H2O. So my Q of H2O is going to equal to the weight of water, 98.75 grams, multiplied by specific heat, 1 calorie per gram degree Celsius, times the change in temperature of the water, which is 14.0 degrees Celsius. Notice grams cancel, degrees Celsius cancel. So we are left with energy units. So the answer is going to be 1,380 calories. Paying attention that there are 3 significant figures in the temperature. That is the weak link, making 3 significant figures in the answer. However, not quite finished. Looking at the data table, we need the answer in kilocalories, not calories. So we can easily convert 1,380 calories times 1 kilocalorie over 1,000 calories. Notice calories cancel, which gives us 1.38 kilocalories. So I can go ahead and write right next door here 1.38 in the box. There we go. Now, this 1.38 calories is the amount of energy given off when we burn half a gram of food. We want to report the energy in kilocalories per 1 gram of food. So we can take 1.38 kilocalories divided by 0.50 grams of food, which is going to equal to 2.8 kilocalories per gram of food. Pay attention, 5.0 grams has two significant figures. So my answer needs two significant figures as well. So I can write into this table 2.8. Make sense? The significant figures are not the same because the weight of the food burned has one less significant figure based on the precision of the balance. I think the most confusing part of the experiment is the calculation that I just performed, but let me go over a few pointers in the experiment before we conclude. So let's look at the procedure. The procedure states to take two 50 milliliter portions of water. Whoops. Let me rewrite this. 2 50 milliliter portions of water to get approximately 100 milliliters. I have added approximately 100 milliliters of water to the can. This happens to be Celsius can on the left side. If we look carefully at the balance, we'll see something. What do we notice? It should say OL or overload. The maximum weight the balance can measure is 100 grams. The density of water is 1 gram per milliliter. 100 milliliters of water weighs approximately 100 grams. Add the weight of the can, and we are over 100 grams. What I ask everyone to do is to fill the can up with 100 milliliters of water approximately. Get to this particular point on the balance and then pour out a little bit of water so that we can actually read the weight. So the weight being 100 grams is not important. What is important is that we know the actual weight in the can. And so if we look at the balance down here, it should be reading, let's see, very close to what? I think it reads 97.44 grams. Often what I find is many people report the weight of water as 50 grams. That is half the amount of water we are supposed to use. If we only have 50 grams of water, there is not going to be enough water inside the can to absorb the energy given off by the food. We are not trying to heat the air inside the can, but rather we want to heat the water inside the can. So make sure we use approximately 100 grams of water. In this case, we are just under so that we can read the weight on the balance. Lastly, look at the picture of the burning food. We want to make sure that the food is fully engulfed in flames before we put it underneath the calorimeter. If we do not have the food fully engulfed in flame, it may go out before it ever gets a chance to heat the water. So what I recommend is the delta T for your H2O should be greater than 10 degrees Celsius. If delta T H2O less than 10 degrees Celsius, repeat the experiment. Everybody should have a bag of food, whether it be the marshmallows, the tortilla chips, or the walnut. Once everything is set up properly, it should be less than 5 minutes to go about repeating the experiment. So a temperature change of less than 10 degrees probably means that the food went out, it extinguished the flame well before we had a chance to burn much of the food.